Okay, hi. I don't know if anybody doesn't know what EMV is and just sort of came in here by random luck. EMV stands for EuroPay Master Visa, and it's the protocol that's spoken between the chip and the payment terminal that you have. The EuroPay thing should already suggest to you how old this is, because EuroPay hasn't not been around for a long time. About myself, I worked for a long time at a big German bank in the credit card processing in the back end, and then I was working for the last several years at a consultancy doing mainly, doing general technical things, but mainly focused on credit card processing back ends, fraud management, stuff like that. And I was involved in several projects where we actually wrote the software that runs on the chip. Since this year, I've been working as an independent contractor and working on a lot of the same sort of topics. The motivation for this talk is kind of weird. It's sort of a strange mixture. It's really basic, really introductory to EMV. On the other hand, it's super low level, so there's a lot of bits and bytes. We're not going to see a lot of pictures or anything. It's going to be a lot of text and numbers. I'm not really revealing any secrets of the credit card industry. I'm not showing any super special hacks. And this stuff is really, really old. I think on the first Congress that I was at, the 18C3, there was already a talk about this. And so the question is, why would you actually want to deal with it? One of the things is this technology is being mandated in the United States soon, so there's going to be a giant uptake in usage. And the other really part of the thing that makes it interesting is that this protocol is so old. And this was always a very pragmatic protocol, and this back in the 80s, so there's not a lot of security in it. I'm also not really going to go into low-level hardware stuff, attacking these chips. I'm not going to go into any attacks on the crypto. And what you'll see, though, is that this protocol is so rudimentary and weird that it's not really necessary. There's so much more that you can do. And it's also, if you were at Carson and Dexter's talk about scraping off the chips and actually taking pictures and probing the chip in operation, that's, I mean, they said this is easy, but this is a lot easier. I mean, you can just look into your own card, see what sort of data is stored on it, and do these own transactions with a card reader that costs maybe $20. So I'm going to go through this is more or less to get you started on doing this stuff yourself. So I'm going to go through a bunch of acronyms and specifications and stuff. I mean, the stuff that the card can do or that it could do in the 80s was really, really rudimentary. So the protocol is actually really easy. The hard thing is, though, that it's a very steep learning curve. There's a lot of weird technology and acronyms and things that aren't really in common usage that you're not really used to. So I'm going to start off with PCSC. PCSC is how you're going to connect a reader to your laptop. Basically, almost all operating support PCSC on some level. Most languages have bindings. The transactions that I'm going to do are with some Ruby code I wrote. This smart card project are the PCSC bindings for Ruby. This demo code that I'm going to be showing, that I'll be talking with this card with, is available in my GitHub repository under 29C3. And while I'm showing URLs, there is this open SCDP smart card shell, which is a JavaScript implementation, which is a lot more feature complete. So if you want to play around with smart cards, that's a really good suggestion. And they also have stuff for dealing with SIMs or the German health card and things like that. So basically, that was already the first point. I mean, you don't need a special terminal. All of the stuff and talking to the card is entirely standardized. You don't need to buy something like this. You can just go to Amazon and get one of these Swiss Army knife card readers that if you're paying $20 for them, you're getting ripped off. And they will work just as good as anything else. So it's a very, very, very low entry barrier to entry. So I'll go ahead and start my little shell, and basically this is just, I can see now I have one reader plugged in. Fantastic, I'll put my card in. And then what is it, dump card data. Show card, show card. That will come later. So this is already the basic interaction with the card. We're connected to the card, and the session has already started at this point. And it's, we're maybe 2 or 3 minutes into the talk. So all of this low-level stuff of how chip cards are dealt with is taken care of in ISO 7816. You don't really have to worry about those standards. You don't really need to get them. If you are really into standards, you need book 3 and 4. They define sort of the low-level characteristics of how the physical layer communication with the card, which is basically just a UART. It's just a simple serial interface. And level 4 is sort of the transport layer. There's the rudimentary how to talk back and forth with the card. Again, you don't need any of this. The next 5 slides will sort of be all you need to know about it. First thing that we saw here, down here, this answer to reset is basically just the ATR is the thing that you will hear. It basically is just the terminal settings, the baud rate and things like that. There's one interesting thing about it if we're approaching it from a really high application level like we are, which is the historical bytes. And the vendor can put anything in there, so sometimes it helps to have those historical bytes to identify who the vendor of a card is that you're dealing with. But you normally don't need to do that because most of the cards, if you look at yours, will have the actual vendor printed on the back of the card. You will see like credit card numbers and stuff from this card. This is a demo card, so you don't need to worry about I'm being a total idiot. And I'm using a demo card. For on the one hand, I don't want my credit card number to be known to you guys, and on the other hand, for the demo cards that get handed out at like trade fairs and stuff, you know the keys that are on the card, so you can reverse engineer the crypto with them. So 78164 describes a couple of further things. First, they have this weird file system-like thing that you don't really need to know much about. But if you see terms like EF, MF, DF, those are either directories. EFs are elementary files. MF is the master start of the file, but don't really, they call it a file system, but don't really think of it as a file system. A file on a smart card can be anything from an application to some sort of cyclic buffer to all sorts of things. But EMV doesn't use a lot of that, so we can skip it. The main thing that you need to know is APDU. APDU is basically just the packets that get exchanged between the card and the host. And it's just a bunch of bytes, which I purposely put an exclamation mark behind it. It really, I mean, you're just basically assembling 5 or 6 bytes, sending them to the card and getting them back. There's very little crypto involved in the communication. So all of the communication that you'll see in my demo, I'm not doing anything special to decrypt what's going on. I mean, these are really the bytes that are getting sent back and forth. So I'll just go through it on one example. If you want to select one of these files, or in this case, an application, there's always a class byte. A class byte of 0 says this APDU select file is defined in the ISO standards. Most of the EMV ones start with 80. That means it's a proprietary APDU. Stuff like that I'm just going to skip over because it's not really that important to dealing with. And then there'll be some instruction bytes. Some APDUs will take parameters, so there's 2 bytes for parameters. Then if you're transmitting data, there's 1 byte for the length of the data. And finally, the data that you want to transmit. So this is basically the application name of a Visa application on a card. What we're doing here is selecting the Visa application to make a payment transaction. There's one more thing that we saw here, that this card speaks in the protocol T equals 0. There's 2 low-level communications protocols defined. As I said, this whole thing is just a UART, and there's 1 character-based way of doing it and 1 block-based doing it. And all that you really need to know is you can't, if you are using T0, you can't send and receive data in the same packet. So if you wanted to have this last LE is length expected. If you expect data back from the card, you have to tell the card how much data you want back. And if you're using t equals 0, you can't send data and expect to receive data in the same packet. We'll see how that will work in just a second. But basically what you really need to know is that the difference doesn't really matter because T1 is complicated. The terminals all speak both, and nobody actually uses T1, at least in payment cards. So just ignore that. So we just learned the select command, and we'll just execute it against the card. I don't know, is this large enough to see, or should I? Yeah. So basically, right here are the bytes that we saw on the slide. And I used a different file name. I used the onepay.sys.ddf01. df is a directory file. But basically, this is just a well-known file name for a file that's called the PSE, the Payment Service Environment, which is basically a table of contents for the card. A card can have several applications, and these are the and the PSE lists the applications that the card wants you to know about and use. So there could be other applications on the card, but there don't necessarily need to be. You don't always need a PSE. We can, the response that we get back, so I said you can't send and respond in the same transaction. What happens when you do that, when you need to do that anyway in t equals 0, is, if this 9,000 is interesting. The card always responds with 2 status words, 1 and 2. And if you get 9,000, that's perfect, that's okay. So that's HTTP 200. Most other status codes mean errors, but basically this select gets a 6126 back, and all the 61 status word 1 error codes mean there's more data coming, and it will be 26 bytes. So basically this is one transaction. You can ignore the second one. The second one gets executed automatically when you get the 6100 response. And it says, please give me back the 26 bytes that you told me that you can give me back. So we can look at the response. This is all tag length value in here, and this is something that's called the file control information. This is basically a metadata that contains data about the file that you just selected. One of the things this one contains is the name of the actual file that we selected. Thanks very much. Just type that in. And this file is also identifiable by a short file ID. Now, the special file has records, and each record basically tells us about one application on the card. So this first record contains, so this card contains 2 applications. One is a Visa debit card and one is a credit card. And so I read the first record out of this PSE file, and it tells me, okay, there's one application that's called Visa debit, and sometimes you get that shown in a terminal that you're paying with, and it also says the priority of that application. So if you need to make a choice terminal, this one has priority 1. So then we can look at check for more records. There's a second application on here, the credit application, that has priority 2. So. And then the terminal will keep doing this until it has a list of all the records. Finally, it gets there's no such record. You can quit looking now. Okay, so that was the basic of how an APDU works. Just the bytes on the screen get sent back and forth in clear text. That's it. And the PCSC libraries have a command, transmit data, and you just give it a raw buffer of data. So it's fairly easy to program, but very low level. So EMV has a huge number of specifications. The main Application framework is defined in books 1, 2, 3, and 4. That's about 800 pages. And I'm just going to skip over really quickly which ones are important and which ones you should look at. Book 1 is maybe interesting because it contains a summary of all of the stuff that's in the ISO norms, how these APDUs are set up, how the low-level UART communication is, how the ATR is set up, and stuff like that. So it's just a review of how this stuff works. That's something that's good to look at. Book 2 is one of the most interesting books. It contains all of the crypto that's done by the card. So the card doesn't get it gets its own keys, but those are derived from master keys from the bank. All of these key derivation algorithms are described in here. All of the certificates that are placed onto the card, the format of these certificates are described in this book too. And the interesting thing is, if you think certificates, usually you think X509 certificates, but in the EMV standards, everything was reinvented and is a little bit different than you would expect it to be. The most important book to look at is book 3, which contains all of the specific APDUs and the instructions that are exchanged with the cards, how those work, how those interact. And one of the most important things, and I put a little heart to emphasize this point, is that there's a data dictionary that explains what all of the tags mean. You know, so here all of the tags are separated, but basically, you don't know what 50 means, but you have to look it up and know that, oh, this is application label. And the data dictionary is really the thing that you work with most when you're dealing with the data in the card. Another thing that you could look at, and this is also freely available on the net, where this TLV bear is defined. This is an International Telecommunications Union standard. And there's some tricky bits to doing TLV the way that they want you to do it. Then there's a book 4, which you can basically ignore. I mean, it's kind of funny because it tells you all sorts of stuff of how you should enter the PIN and how you could implement a virtual machine, whether you should interpret bytecode or translate it into the native instruction set of your terminal's hardware architecture, all the way to what the receipt is supposed to look like that the thing prints. But it fails to mention stuff like what data of the transactions the terminal is supposed to save to present to the bank later. It's really weird. I've never used it. It's sort of fun to skim through, but it's not useful. CPS is, you probably won't ever need it. This is the application that's on the card before it's in the field that in the personalization bureau will be used to place your personal data onto the card. But if you're dealing with, if you want to take a closer look at cards, this is something useful to look at because it provides some really useful insight of how data is structured in the card and what data is actually placed on it. Finally, there is CPA. So these books 1 through 4, they describe a general framework of how to make applications for financial transactions. They don't actually describe an implementation. EMV published one standard for an application, and this is sort of interesting to look at to see what actually goes on. Books 1 through 4 describe really well the external interface, but they don't really give you a good indication of what the card is supposed to do internally, how it's supposed to check the data. They also leave open a lot of data structures and what they mean. They just say, what we'll see later, for example, you get card verification results, which is a big bitmap of literal checks that the card did. But it doesn't say what each bit is supposed to mean. The actual implementation specifies that sort of information. There's also what you will come across CCD, which is also called Dublin Core. It's common core definitions, and that's spread out through all of the standards. It specifies some of the missing pieces. So you can, it will specify a base card verification results bit field, what you should put in there. The specifications that would be most interesting are, but you don't really need at the level that we're dealing with, are the MChip and BSDC specifications. Those are the concrete implementations for MasterCard and Visa. Unfortunately, those are proprietary and you can't really get at those. With MasterCard, you can't even get the names or the current versions of them unless you're a MasterCard vendor. Visa, you can at least get a list of what the current specifications are called and which ones are available, but you'll have a hard time finding them. Okay, so we've gone over all the specifications, and we're going to go into actually what happens and try to get 1 pound off of this card. So the general flow of the transactions in normal human terms would be card and terminal introduce each other, figure out which application to use. So that's the part we've done so far. Then this is what I call worst first date ever. It's not just tell me a little bit about yourself, but it's tell me what questions to ask you about myself. That's what the terminal says to the card, and then the card responds with a number of records that it wants the terminal to read. It doesn't really check that it reads those records or only those records, but that's how the mechanism works, just to introduce it. Then there's some simple mechanisms to make sure that the data that the card returns are actually valid data and that they come from a real bank and stuff like that. Then there's what's called cardholder verification. So that might be something as simple as you sign a piece of paper. So it happens totally offline. It might be something that the card checks the PIN, or that the terminal or the ATM sends the PIN to the bank to be checked and gets a response back. And finally, the card will generate a cryptogram with a symmetric secret key that the merchant who owns the terminal can later present to the bank to prove that this card was actually involved in the transaction. So one of the common misconceptions is that the chip is basically just a dumb storage of data that's going on. So that's not really what's happening. The chip itself is a little computer, and what theoretically happens, there's a key on the card that can't be extracted. And the terminal gives that key a random number. It encrypts that random number, and that way the merchant can prove that this card was actually physically involved in the transaction, and nobody just copied the card number. Okay, so we'll do the tell me what to tell you about myself, or whatever I called it. So first we want to select this, the VSDC application, which we figured out, the file name of which we figured out from reading the PSC. And we get back another thing of file information data. Basically the same thing again. It tells me the file name, it tells me the application labels and some proprietary discretionary stuff. As soon as you see issuer discretionary or something like that, you know you can ignore it. And it also contains an application priority indicator that was in the PSC as well. So a lot of cards don't actually have this PSC. The terminal will just try to select the applications directly, and we'll put them in the right order. So after we've selected, the first thing we do is a get processing options command. And we can see this is pretty opaque data. This is response message template format 1, whatever that means. But this is kind of the most important part. So get processing options, there can be something that's called a processing data object list, which would be returned in the FCI in the select. That wasn't the case here. That will be the card telling the terminal what sort of data the terminal should provide to it. So it could say, please, when you call this get processing options command, tell me what sort of terminal type you are. Are you an ATM? Are you a candy vending machine? Or whatever. What the card returns are two pieces of data, AIP and AFL. And this is format 1. You remembered that from the response message template format 1. And it contains 2 bytes of AIP So, and the second one is really easy to explain because all those bits in there are reserved for future use, so they're always 0. And in this case, 5C, I've circled all the bits out of the specifications, what they mean. This card supports STA, cardholder verification is supported. That's always supported. Terminal risk management is to be performed. So the card tells the terminal kind of what to do, which you need to keep in the back of your head. It does that quite a lot. And issuer authentication is supported. So most of these things don't really make sense because issuer authentication is always supported. Cardholder verification is always supported. And the thing to explain here is DDA and CDA down here in the bottom. This card only supports SDA. That's static data analysis, and that is how, in the next step, once we have all the data, how we check that this data is actually from the bank. In static data authentication, all of the data that's to be authenticated is hashed. That hash is put into a certificate that's signed by the issuer, and so I can get all the data off of the card, hash it, decrypt the certificate, make sure the hashes are identical, and then I can see, well, at least this is the data that the issuer intended to be on this card. Why this is important, we'll see in a minute. Unfortunately, this is because it's static, it makes the card sort of trivial to clone because the certificate is on the card. And you can just read it off of the card, and you can just write it onto another card. And so any copy that you make of this card will automatically have a correct certificate. DDA will also have a public key mechanism where the terminal can give the card a random number, and it will encrypt that with its private key, and then the terminal can decrypt it so it knows all of the data is correct, and this card is actually in possession of a secret that's supposed to be on it that I can verify. Because the general key on the card is symmetric. Only the bank can verify that. The terminal can never check if any cryptogram that the card provides is actually authentic or real. But again, this was a pragmatic protocol back in the 80s, and back then calculating RSA or something like that was quite expensive. Putting a crypto processor on the cards is still quite expensive. So you can save 50 cents per card or something by not supporting it. I think they're starting to mandate using it now, but this is still a fairly recent card. So the next point, I'm not going to go into it too much. This is the application file locator, and it's a list of 4-byte entries. So these are 3 application file locator entries. The first byte of each entry contains the short file ID that the card wants you to read. And for some reason, it's shifted by 3. So it's the high 5 bytes of that. The second byte is the first record to start reading. The next byte is the last record that you're to read. So this basically means short file ID 1, read the first record only. Short file ID, read records 1 to 3. Short file ID 3, read records 1 and 2. And the last byte here is interesting because that indicates which record will actually go into the static data authentication. So even though this isn't really a safe way of authenticating the card, not even all of the data that's being read from the card is being authenticated. So, let's see here, read records. So it goes through here, that parts the AFL, and it read records, short file ID record, short file ID 1, record 1, 2, 1, 2, and 3. And 2 records from short file ID 3. So I did that correctly in the slides. This record here, short file ID 3, record 1, is the only one that is ever authenticated. So even with this, and I still have the last one in the buffer, so we can look at that, and that's really all of this information that we'll go into more detail like the currency that the card expects, the expiration date and the effective date of the card, things like that aren't ever checked for authenticity in this specific card. Usually this information will also go into the certificates. So this is where the dump card data came from. So this is all the data that we collected from the card. The first field is fairly simple. It's the cardholder name. Your name would be in that field. Here it's simply one because it's a marketing thing. This is quite interesting. And also as a general attack, track 2 and track 1 data, if you've done anything with cards, this might seem familiar because this is how magnetic stripes are structured. So basically this card, the smart card provides the precise data that's also on the magnetic card. So if you can read out all of this data, you have enough data to clone the magnetic stripe. And it's already perfectly formatted in the way that it's supposed to be formatted on the magnetic stripe. The reason for this is that the bank backend systems are very, very old. And they don't necessarily check all of this card data that's coming because it's more complicated. And so what you can do is you can just take, on some intermediary system, throw away everything else but these track data things and then process the transaction as if it were a normal magnetic stripe-based transaction. Or you can hire Visa or MasterCard to do something called STIP, where they will have a system in front of your own backend, check all of the chip stuff for you, and just give you the magnetic stripe data. Or you can just ignore to do that and just not check the EMV stuff at all. Then there's the issuer's certificate. The terminals have lots of CA certificates. Those sign these issuer certificates, and you need the issuer certificate to get to be able to decrypt the certificate that contains the hash with the data that's on the card. And the rest of the data is basically standard. The PAN is the card number, the expiration date, the effective date. This is a card that's issued in England in pounds, and I'll go into what the other things mean right here. Service code, again, is something that comes from magnetic stripes. That was one of the things on here. I'm going to skip that because we're kind of, I don't know if I'll even make it. The first thing that's interesting is application usage control, which is, again, similar to AIP. It's a bunch of bits that say what this card may be used for. There's two bytes in it. The first one is FF, so the card could be used for all of these things, which, and again, these categories are really arbitrary. You know, I mean, why differentiate between goods and services? Sometimes differentiating between domestic and international might make sense, but why have a card that I can pay with to get my hair cut, but I can't buy a bottle of shampoo with it? You know, this is goods and services. So it's hard to even configure these things or figure out what they're good for. And the second byte is, in this specific case, because it's also, this was the debit card, it will allow domestic, so if you're in your own home country, you can get cash back, which would be, you pay for £10 at the store, and you say, well, please give me 20 back. And you might not know where you are internationally, so you might not trust stores anywhere else to do that validly. So, I mean, I can see how that could make sense. The next thing was the CVM list. It starts off with 2 amounts, and this is a really, really important one. But these 2 amounts aren't ever used, so I'm going to skip over this. And the next is a variable length list. Each entry is 2 bytes long, so the color coding is 1 entry. And these tell the terminal what sort of cardholder verifications it should attempt to do under what circumstances. The first byte in each entry describes the actual cardholder verification that the card supports. So in this case, this will allow plain text PIN verification by the card. I can send the card the PIN and it will tell me whether it was correct or not. It will support signature. It will support the PIN being sent to the bank and being checked there. And finally, this is the nicest one, none. It will support that as well. And basically the terminal will go through and basically if it can fulfill one of the conditions, and these are the next one, the second one is under which conditions should we use this? And And if it can fulfill it, it will do that, else it will try the next one all the way to the end. So basically these conditions say, do pin verification unencrypted if you can, do signature if you can, else send the pin to the bank if you can, and if not, don't worry about it. So this is quite interesting because, well, we're sort of gonna authenticate the card, but the card doesn't know what sort of terminal, it doesn't know if it's in a real terminal or if it's just sticking in a cheap card reader at some hacker conference. So it can't really trust that I will actually do these verification methods, and especially not in this order provided. Another thing to note here, and this was one of the important hacks recently. As I said, all of the data being sent back and forth between the card and the reader is completely unencrypted. There's no non-repudiation. The data is not MAC'd, so this is a perfect target for man-in-the-middle attacks. And so the chip cards were supposed to help to mitigate against skimming type attacks. But it turned out it's a lot easier to actually insert a skimmer into, say, an ATM, and then just basically read the communication between the card and the ATM. Now, on top of that, it's also fairly simple to modify this communication. So one of the hacks that was quite interesting, so we saw that when we read all the data, we already have the magnetic stripe data ready for cloning and making our own card that we can use in Romania or somewhere at an ATM, but now we want the PIN. And technically, cards aren't allowed to accept clear text, unencrypted pins at ATMs. I don't know why they're allowed to do it elsewhere. I don't know. Nobody would ever install a skimmer in anything else. But so this hack was basically, there was a man-in-the-middle attack, a skimmer or a shim type attack, that whenever the card sent the CVM list to the ATM, it would say, I only support unencrypted PIN. Please give me the PIN unencrypted. And even though the ATMs wouldn't actually be allowed to do that, I don't know, maybe because they used like candy vending machine firmware in the ATM, they decided, okay, well, if you say, send it to me unencrypted, I'll just send it to you unencrypted, and then you have the PIN and the magnetic stripe data, and if you have a nice GSM module in your shim, then you can just send that off and immediately run to the next ATM to get money. So, and the whole, like, I trust the terminal thing goes on here. These are issuer action codes, and we have to sort of, this gets a little bit hairy. I'm only going to skim over the details. Basically, while the terminal, for the terminal to think about what it's going to do, it fills out this bitmap. And basically it has little bits for each thing that happens. Like if the static data authentication fails, it will set that bit. If the card is expired, it will set a bit here. And there's basically 5 bytes of bitmaps that can be set, and if any of these correspond, this condition will take effect. So if this bit will get set while the terminal is verifying the card, the card would like the terminal to decline the transaction immediately. So if we have a look, that is requested service not allowed for card product. So the card might say, I don't do domestic services, so please decline that, something like that. If any of these bits are set, the card, the terminal should ask the card to go online. And the card will generate a cryptogram that will get sent to the bank. The bank will decide whether the transaction is authorized or not, and it comes back. So these are the conditions under which that takes place, and default is quite interesting because it's, if you should go online, but you can't, you can still do the transaction. You can try to do the card do the transaction offline with the card. And so I mean, the thing to look at here would be the difference between those. So only in this bit will the card actually have to go online. And that is transaction selected randomly for online processing. So again, these are really weird combinations of things. So if the merchant forced the transaction online, if you pressed the button and said, I want this to be authorized by the bank, the terminal can still try to, according to this information, the terminal could still try to do it offline. But if there's some sort of random selection mechanism for risk purposes to take every 10th transaction and send that to the bank, and it can't do it, then it could still, it doesn't really make sense. So, okay, so we're going to confirm the data, and I'm basically just we'll just show one of these. So we had that issue. We had the issuer certificate. If we decrypt that with the with Visa Certificate Authority certificate, we get this, which basically still looks like random bytes. Skip over the details. So, but this is described in book 2 because it's crypto related and certificate related stuff. And you can see there's a header 6A and a hex value BC, and there's a bunch of metadata about the certificate, and then the issuer's public key modulus. So if we look at the data more specifically, we can see the header 6A, the trailer BC, there's an expiration date in there, and the interesting part is this bit in the middle, which is actually not the entire issuer public key, because it could be just as long as the key that's on the, as the CA key. And it's okay, so if you have a 1024-bit CA key and you want to encrypt something with it, it has to be in multiples of 1024 bits as well. So if the issuer's key is also 1024 bits, you can't encrypt it all with all of this metadata, and you have to leave a bit of the issuer's public key out. So this is called the remainder, which was also in here. And so to verify this, basically you have to take the leftmost digits, then you put the remainder on it, then you hash it, and then you make sure that this hash corresponds. Instead of putting the whole key into the card and just putting the hash in there, they make things rather difficult to deal with. So this SDA certificate, I won't go into too much. It's very similar. If we decoded it, it would look like this. It has tons and tons of padding, and then it only contains a hash. And this hash is basically a hash over the record that was marked in the AFL, the application file locator, that has the weird short file ID shifted by 3 in it, if you remember it. It had one marker that says, this is the data to authenticate, which in our case was just the card holder, the card number. And this is basically a hash over that data, so you can take that record, hash it, decrypt the certificate, make sure the hash is coincide, and then you know this is the way that the issuer wanted actually put the data onto the card. If this card supported public key encryption, there would also be one further certificate on the card, which contains the card's public key. And if it's supported, and there's an option to put a third public key on there, which will be used to encrypt the PIN. Basically what happens is the card's public key certificate will also contain all of the static data, but it will also have a key inside of it. So you can recover that key, and then you send the card a random number. The card will encrypt that random number with the private half of that key. You can decrypt it, and then you don't only know that the data that's on the card is what the issuer intended to be on the card, but that the card also contains the corresponding secret and is able to do calculations with it. This is, if you want to have a look at that, it's also in book 3, and the command is internal authenticate. So finally, we confirmed the card holder. What we did we saw this card does offline unencrypted PIN. The PIN is formatted in this very special way. 2 is an indicator that this is done in a very special way. 4 is the length of the PIN, and then you have the PIN is BCD coded. So you could have up to 2, 3, 4, 5, 6. I think this is you could have like a 12-digit PIN if you wanted to on the card. So then we just say verify the PIN. I don't know if I need to put PIN in. Yep, and it was 1, 2, 3, 4, which is incidentally the combination on my luggage. And the 9000 again, that's always the status word that says OK. So this is the right pin. As the terminal now knows, well, this has to be a legitimate card holder. So finally, we need to seal the deal. Now we had, I left out two things, and that was the C doll. We've heard doll before, and now we get to see one. So this is basically lots of tag length value stuff. I've, again, color-coded the differences. They're all stuck together. And this tells the terminal what data, what transaction data and further data it expects from it to generate its cryptogram with. So basically it wants the amount other would be for cashback. It wants the country that it's in and the currency code, so it can do offline checks that it hasn't already authorized too much data on offline. Again, transaction date, you really don't know what it's going to do with it because this card is expired for like 3 years, and it doesn't really know that because I tell it that it's still 2010. And it wants a random number in there. So that's the data that we stick together, and then we have to request a type of, according to the terminal verification results and the issuer action codes that we saw earlier, we have to decide, do we want to request this transaction to be declined? Do we want it to be authorized by the bank, or would we like the card to try to approve it? So if we put this together, which I've already done for the sake of time, these are all the fields. So amount 1, we want to get £1. Amount 2, we're not going to do cashback, we're in the UK. Currency is the same. It's October 10th, 2010. Transaction type is 00 is purchase. Then this number is, of course, very random. And I stick all of that together, and that will be the CDOL data that I sent to the card. And then I can do a first generate a C. And so, and the response I get is also sort of random. This is the clarification for the response, and this is different, unfortunately. So the first bit is the cryptogram information data, and that will tell me, just because I want the card to authorize something online, doesn't mean it has to. It can also say I want to talk to the bank, or I'm going to just decline it right away. So this basically says whether it was authorized or not. The application transaction counter is a lifetime counter. The card can never do more than 65,000 whatever transactions. The bit in the middle is the actual cryptogram, and the issuer application data is what contains the card verification results. We're not going to look at that. So this cryptogram information data that I got when I was trying it out with this card was 8, so it was an ARQC. The card wanted to go online. In this case, we got a 40. So we have a TC, and the card approved our transaction, so we're done. What we would do in case we wanted to go online, there's a CDOL2 for a second generate AC, and that would want, in this case, the authorization response code from the bank, and we can just tell it, and that worked just fine. We can just tell it 00, bank said OK. Typically there'll also be some sort of cryptogram from the bank coming back, and the card will want that, and we'll parse it. So just in order to, so this is basically what I got back now. This is but we can skip that. So in conclusion, I mean, this is a really, really old protocol. It doesn't really mitigate the proper risks that go against it. And for example, when you're making these cards, you take them to laboratories, the chips get stripped, and they shoot lasers at it, hoping that they'll flip some sort of bit that will make the card reveal its secret key, its symmetric secret key, which is ridiculous because basically, if I steal your card, I mean, the options are, oh, I can get a laboratory for 500,000 euros and shoot lasers at it and do all sorts of stuff, or I can just hit you over the head until you tell me your PIN. Because that one key that I extract from your card will allow me to clone your card and not anything else. So all of these, so the crypto and the hardware is fairly solid. You can probably find lots of stuff too, depending on which card you're using. But just the general problems in the protocol are much larger. And one of the big problems is that these are being transferred to new technology as well. So the banks are really, or the card organizations are very reluctant to part with this legacy technology. All of the contactless stuff that's coming into the field now work identically. There's no transport layer protection to those either, and they switch the commands around a little bit, but basically it's exactly like what you saw. So that was it. If somebody has questions, I am also available after the talk. These slides and the software I showed should be available on the wiki. I don't know if they're uploaded yet. Yeah, and if anybody has any questions, I'd be happy to.
If you have any questions, please line up at the microphones.
Perfect.
We have one question on the right.
Hi, if I understood you correctly, it's possible to just use the magnetic stripe data to do a transaction. Is that right?
Well, if you're in Europe, at least you're. So what's coming out now is a lot of these things like Square, and in Europe there's lots of clones off of that. And Square worked well because it just uses the magnetic stripe data. In the United States, cards only have magnetic stripe data. The whole point of these credit card scheme was to have one card that you can use anywhere in the whole world. So they can't really mandate that the terminals in use can only do EMV, because then Americans couldn't buy stuff here. And the other way around, they can't not put magnetic stripes on European cards, because then you couldn't go to the States and buy something. And basically, you can also just break them. There was a year 2010 bug in German cards, and the easiest way to get around it was just to smash the chip and break it, and then it would fall back to magnetic stripe. So yeah, you still always have that weakest link of processing through the magnetic stripe data.
Yeah, what I was wondering about is whether it's possible to tamper with the magnetic stripe data that's sent.
Oh yeah.
And thereby check whether banks actually check all the crypto things, or whether banks just do the easiest thing, take the magnetic stripe data that's sent, and don't implement all of the crypto things on the bank side. Is it possible to do experiments in such a way or not?
Well, I mean, it would be, I wouldn't do it because I mean, that would be illegal, right? And you would also have to do it in the field, you know, so playing around with this at home is absolutely no risk, because it's your card, and even if you break it, if playing around with it, you take it to the bank, they won't see that anything's wrong with the chip because they can't look inside it. Nobody understands this stuff, and they'll just say, oh, you know, but we want you to use your card to buy this, and you'll get a new card immediately. So there's no risk in that. You could, that would be a good way to find out whether banks are actually checking the magnetic stripe data, but you would have to alter the data on the. Well, okay, if you clone the chip, make your own card. Just use random keys for the cryptogram stuff. Then you could check whether they actually check the cryptogram, which doesn't always happen.
Yeah, it was more like a thought experiment.
Whether
it would be possible to test what the banks actually do.
That would be a good way to test it. Yes,
okay,
but
thank you.
They would also. It'd be easy to get caught as well.
Are there any more questions? No, please give a warm applause to our speaker, Tim Becker.
Hello, hello.
Thank you.
One more question from the left-hand micro.
I have a short question. what part of the stuff on the card is actually signed? So, for example, if my card doesn't support cashbacks, can I put it into a reader and set a 1 in there and go to the shop and get a cashback?
That would be an interesting thing to look at for individual cards. I've never found anywhere where there's some suggestions of what you should sign, but not everybody necessarily does that. So for example, in this card, which is, I mean, it's a demo card from Visa, that's obviously what they kind of expect you to do, they didn't sign any of this stuff, and that included the CDAL data that the card needs to be sent to generate the cryptogram, and more importantly, it included these risk action codes, you know, like when are you supposed to decline a transaction, when are you supposed to do that? And what it also didn't include was, what it certainly didn't include, because that's not usually in these records, is the application file locator that tells the terminal what data to read in the first place. So you're authenticating something, but you read that from the card and you don't really have any way to know that that's actually what the card wanted you to read. So it also wasn't done here, for example, the certificate authority public key, the way that you get that back. So if those are ever revoked, you could put in, you could use another key because that one was cracked. And the part that I forgot to mention, what's quite important, I said that the card isn't really a dumb storage for data, what most people think. All of the stuff that we got with read record, so all of this card data, that part is just a dumb storage. So the card doesn't know about any of this. The card doesn't know its own card number. It's just stored somewhere in a filing cabinet, but it doesn't use that for any calculations. It doesn't know about any of these action codes, so it doesn't know if the terminal is actually doing the right thing or not. But yeah, the way that what parts are actually encrypted, and people forget to put important fields into the certificates all the time. Or not all the time. I mean, they shouldn't. But I'm sure you could find cards where vital pieces are not actually authenticated. Because this is really complicated. I mean, try to put together stuff like this. So it's like there are these guidance rules, but nobody, it's just like, well, okay, I'll do it like it says in the document. And the people that make those decisions, sorry, last sentence, and the people who make those decisions a lot of the times, I mean, either they're really, really highly knowledgeable at banks, but a lot of the time they're just the project manager for some credit card project, and the normal decisions they make is what picture goes on the card. And then you expect them to like figure out all of these bitmaps. I mean, that's not the usual case, but that happens as well. So thank you very much, and thank you.
There is another question from the right-hand microphone.
Not really a question, more like a comment. You mentioned that that standard didn't tell anything about what gets sent to the bank. For learning more about it, it's ISO 5853. 8583, yeah. Which is funnily supposed to be a standard, but it's somewhat different in different countries, and that leads to interesting hassle. And another thing was you seemed to be wondering about why they would be caring about whether something is goods or services. There are some payment cards that only accept, for example, paying for services and even paying for certain kind of services. For example, I have a card in my wallet that only lets me pay for lunch.
Ah, okay. Yeah, that would make sense.
Yeah.
Internationally or domestically?
At the moment, unfortunately, only in Finland, but maybe the company that made it will spread.
So 8583 is at the last level towards the banks or the card institutions, the protocol that will get spoken, and that's even more than EMV. It's kind of like XML. It just defines a general framework of how such a protocol should look, and that's why every single implementation is different. And it's really complicated and convoluted, so the people who do the entire specifications of the concrete protocols usually screw stuff up or make it very difficult to deal with.
Any more questions? Doesn't look like it. Well, give a nice round of applause